Okay, this presentation we're going to talk about limiting reactants or reagents and percent yield. So in chemical reactions, there's actually a limit as to how much product can be produced. And the reason being is that one of the substances may get used up, meaning the reactants may get used up first before the other one does. And this substance that gets used up first is called a limiting reagent, or it can be also referred to as the limiting reactant. Either one is acceptable. So I often interchange these terms and call this limiting reactant because it is on the reactant side. And the limiting reactant determines the amount of product that will be formed because it's limiting. So the limiting reagent limits the amount of product produced. You'll hear me say this a lot in class. Okay, but that's the key. The limiting reagent limits the amount of product produced, or the limiting reactant limits the amount of product produced. So let's try an example here. So this is a pretty simple equation. We got 4 moles of sodium reacting with diatomic oxygen to form 2 moles of sodium oxide. So let's say we begin with 46 grams of sodium and 32 grams of oxygen. We want to know how much sodium oxide will actually be produced. Now notice this is way different than the other stoichiometry problems you've done up to this point because now we have 2 masses. We're saying we've got 46 grams of this and 32 grams of this, and we want to know how many grams of the sodium oxide we're going to produce. So which one of these, the 46 grams of sodium or the 32 grams, is going to be the limiting reagent, meaning what's going to limit the amount of product that is produced? So the way that I solve these is you're going to be required to do 2 equations, okay? And you're going to have to do a comparison between them. So let me show you what I do. So first we need to determine the limiting reactant or reagent because you're given 2 masses. So figure out whichever reactant produces the least amount of the product is the one that is going to be limiting. And therefore, whatever it produces is going to be the amount of product that you can form, maximum-wise. Okay, so let me show you how to do this. So here's the same problem again, just in a smaller format so that I can fit it on the screen and be able to show you the work that's associated with it. So what we're going to do is we're going to start with our 46 grams of sodium. Now what I want to do is I want to figure out how much of the product I'm going to make based upon my 46 grams of sodium. So what I'm going to do is convert my grams into moles. Remember, the steps to stoichiometry, number 1 is a balanced equation. We've got that. Step number 2, we need to think in the unit of the mole. So 23 grams of sodium is 1 mole of sodium. Nothing more than the molar mass. The grams of sodium cancel out. Now, what we want to do is figure out how much of the sodium oxide we're going to produce. So, for every 4 moles of sodium, I'll produce 2 moles of sodium oxide. Okay? So, if you can see here, now my moles of sodium cancel out. Where'd I get this? Well, this is my, again, mole ratio. And I got this from the balanced equation. And then what I'm going to do is I'm going to convert it back to grams. So for every 1 mole of sodium oxide, it has a molar mass of 62 grams Na2O. Again, this is the molar mass, folks, the molar mass. So the moles of sodium oxide cancel out. When I do my math, I end up with 62 grams of sodium oxide. So, starting with 46 grams of sodium, I will produce 62 grams of sodium oxide. That's one part. Now, that's how much sodium will produce sodium oxide. But we were also given 32 grams of oxygen. So we need to see how much the oxygen will produce for sodium oxide. So start with your 32 grams of oxygen. We've got our balanced equation. We need to think in the unit of the mole. So 32 grams of oxygen, this is just molar mass, is 1 mole of oxygen. Then we use our mole ratio from our balanced equation. For every 1 mole of oxygen, it will produce 2 moles of sodium oxide. Grams of oxygen cancel out, moles of oxygen cancel out, and then what I need to do is then convert our moles of oxygen, or sorry, moles of sodium oxide into grams of sodium oxide. The moles of sodium oxide cancel out. And when I look at my results, I end up with a value of 124 grams of sodium oxide. Now, that's produced from 32 grams of oxygen. So, which is our limiting reagent? If you said the sodium is our limiting, you're correct, because it limits the amount of product that we produce. The maximum amount of sodium oxide that we can produce is 62 grams. That's the maximum, because the sodium will get used up faster than the oxygen will. And therefore now we know how much of the sodium oxide will be produced. So, if we go a little further, it says which reactant is the limiting reagent or reactant. So, which one is it? We decided it was the sodium. Now it says which substance is in excess. Well, excess is another word for just leftovers. So which one's going to have leftovers? Well, all the sodium is going to be used up. But there's going to be leftover oxygen. So this is going to be in excess, the other reactant. Now the big question is, by how much? So in order to determine how much is in excess, we need to figure out actually how much we actually used. We know how much we have, but we need to figure out how much we used. So the limiting reactant is the one we're going to start with. That's what determines the amount of excess used and then how much is left over. So we're going to start with our, if we go back up, we're going to start with our 46 grams of sodium. Right here, 46 grams of sodium. So 46 grams of sodium. We need to convert that into, guess what, you know it, mole. So grams of sodium is 23, 1 mole of sodium. Now using our mole ratio from our balanced equation, let's go back. We need to convert our moles of sodium into moles of oxygen. Moles of oxygen. So look right here. For every 4 moles of sodium, 1 mole of oxygen. So every 4 moles of sodium, 1 mole of O2. And then we want to compare the masses. So for every 1 mole of oxygen, there are 32 grams of oxygen. So the grams of sodium cancel out, the moles of sodium cancel out, and the moles of oxygen cancel out. So when I do my math here, I end up with 16 grams of O2. This is how much was actually used. So how much did I have to start with? Well, going back to the original problem, it was 32 grams of O2. But I used 16 grams of oxygen, which means I'm going to subtract 16 grams of oxygen, which I got from here. So when I subtract those, that means I have 16 grams of oxygen in excess, meaning leftover. Now, a lot of times what scientists want to do is be able to determine how well they did their chemical reaction. And we're always trying to get the highest percent yield. This would be like you on a test. Theoretically, everyone on a test should get 100%. They should get all of them correct. But in actuality, a lot of people get different grades. You might miss 1 or 2 questions, which would alter your percent yield, meaning your percent that you got correct. So what this equation does is it allows you to determine how well you performed your experiment by taking your actual yield, what you actually got through experimentation, to what you theoretically should get, and this is based upon a calculation. Okay, so looking at this, it says after performing the experiment, you collected 40 grams of sodium oxide. What is the percent yield? Well, what did you actually get? It tells you right here, 40 grams. Okay, so percent yield is equal to, 40 grams of sodium oxide. Now, in theory, what did you get? Theoretically, what should you have gotten? Well, that means we need to go back to our original problem here where we determined how much sodium oxide we should produce, and that would be 62 grams. That's how much we should produce. So that's theoretical because this was based on a calculation. So we're going to put that 62 grams here of sodium oxide. And then we're going to multiply it by 100 to get us our percent yield. So we're going to take 40 and divide it by 62, multiply it by 100. So we ended up with 64.5% yield. Not very good. Really what we're trying to strive for is anything greater than 90% is considered to be good. And that's how we do limiting reactants and percent yield.